What is a structure? Try to give a few examples in your head first. Done? Okay, odds are you thought of one of these. Maybe you thought of engineering feats like bridges or buildings and the like. Maybe you thought of public transit or otherwise city planning related stuff like train lines, bus lines, subway lines, tram lines, airplane routes, and so on and so forth. Maybe you thought of relationships between people, like family trees, governments, corporations, power dynamics, etc. Maybe you thought of more academic stuff, like sentence structures, algebraic structures, etc. Or maybe you even thought of artistic stuff, like sonatas, haikus, operas, concept albums, you name it. Regardless of what you thought of, what do you think structures these structures? It's clearly not just their components, right? Public transit networks aren't only stations. There are different ways to go from point A to point B, all of which have their own merit, but most importantly, aren't equivalent in any reasonable sense. Likewise, you can't listen to a concept album and shuffle. The exact succession of songs actually matters, which isn't necessarily the case in regular albums, which in itself is a kind of structure in its own, isn't it? Likewise, a family isn't just a bunch of individuals. The way each individual is connected to one another in the family tree actually matters. So, in fact, what structures a structure is the conjunction of that of which it's constituted with the way these components are linked to one another. This is why you can read, according to Wikipedia, that a structure is the arrangement and organization of interrelated elements. If we're trying to be as minimalistic as possible, it will seem that a structure, in a very broad sense, can be captured by the following elements. A class of points, each with different names, a class of arrows, each with different names as well, all of which have a distinct endpoint or target, and a distinct start point or source. If we want to describe a two-way link, we just need two one-sided arrows. If we want to describe links between three objects, you can use 3 arrows, 6 arrows, or any number of them, depending on how thorough you want to be and what you want to actually look up. More generally, if you want to describe any kind of linking pattern between any number of objects, using only one-way arrows is pretty much enough. A sufficient way of understanding structures like a bunch of arrows, essentially, is what we call a quiver. And no, I'm not joking. Most of the time, though, when we design a quiver, we usually think about the more direct relationships between these different components, for efficiency's sake, mostly. A perfect example of that is family trees. One can put an arrow from each parent to each of their children, and an arrow from each child to both of their parents. Just for readability's sake, we'll draw parent-to-child arrows red and child-to-parent ones blue. Out of this, we can essentially define every family blood relationship by following arrows heads to tails. So, a sibling of yours is a child of both of your parents, while a half-sibling is a child of either one. A nephew of yours is a masculine child of one of your siblings, while a niece is a feminine one. A cousin of yours is a child of one of your parents' siblings, a grandparent is the parent of one of your parents, etc. More rigorously, following arrows heads to tails essentially maps out a path, from which we can identify the following data. We start at a specific point on the quiver, which we call the source of the path. We also end at some specific point, known as its target. But what truly makes it a path is the following component. We also have an ordered list of arrows, in which every arrow targets the source of the next. Moreover, the first arrow's source must be the source of the path, and the last arrow's target must be the target of the path. In the eventual case you stay in place and don't actually follow any arrows, you can still make up a path. It simply has an empty ordered list as its last component. So in the eventual case, your list is actually empty, means you stay in place. So in that case, we demand that the source and target of the path actually be equal. Let's go with paths, which we really couldn't do in any satisfying way with regular quiver arrows. Then we can glue routes together to get a new route, as long as they follow one another as to tails, that is. Everything here helps us define what a free category is over a given quiver, which is the data of a new underlying quiver, such that its class of points is that of the original quivers, but its class of arrows is now the class of paths over the arrows of the original quiver. On top of that, we equip that quiver with this gluing operation over paths, the one we quickly described earlier. Note, for the nerdy among you, that this list gluing operation takes care of associativity, but that's for a future video, I think. Probably, hopefully. Free categories are a pretty natural extension of quivers, and serve mostly just as much as a model for what a structure is that quivers do. Now that we've defined what a free category is, one may obviously wonder what even is a category, or at least what meaning we confer to it in that context. The main difference between the two is that some paths may actually be treated as equivalent, be it for they yield the same thing, or any other criterion one may have in mind. For example, adding 2 and then subtracting 2 yields the same result as doing nothing. Even though we've not used the same path, we'll essentially come to the same result regardless, so one might want to consider these as equivalent paths at the very least. The main concern is that we technically don't have a notion of paths cancelling each other out, how adding 2 and subtracting 2 should cancel each other out, if you're in a free category at least. Defining a notion of equivalence over paths require 5 rules, all of which are pretty reasonable, I think, but I feel that we kind of have to go through them at least. First, we have reflexivity, which means any path must be equivalent to itself. Then we have symmetry, which means that if a path A is equivalent to path B, then B is equivalent to A. If a path A is equivalent to path B, and B is equivalent to path C, then A is equivalent to C. These 3 rules already explain what equivalence usually is, but we have to go a little further because we're specifying that we want path equivalence. So now what do we want? Well, the 4th rule will be that we want each class of equivalent paths to have a definite source and target, so that they can be used as arrows in a new, stronger quiver. To do so, we demand that 2 paths can only be equivalent if they share the same source and share the same targets as well. You can't have a path from Paris to London be equivalent to a path from Washington to Moscow. And finally, we want to preserve this gluing luxury that paths provided us with, by being able to glue these classes of equivalent paths together. To do so, we demand that if we have 2 paths that are equivalent, and we glue the same paths onto each of them in the same pattern and everything, these paths should also be equivalent. For example, adding 2 and subtracting 1 equates to adding 1, and dividing by 1/2 is the same as multiplying by 2, so we should expect that adding 2 and subtracting 1 then dividing by 1/2 be the same as adding 1 and then multiplying by 2. Just as a heads up though, saying classes of equivalent paths every time is not only pretty lengthy and tedious, but it's also non-standard. In fact, category theorists usually call them morphisms. First, because it's much shorter, and second, because the very word path isn't actually standard either. Textbooks rather just call them morphisms in free category. That's just a kind of nickname I give them. We can now define what a category is, in the category theoretical sense at least, as given by the following data. We have a new underlying quiver, again, such that its class of points is that of the original quivers, again. Its class of arrows is now the class of morphisms which themselves can be seen as classes of equivalent paths. On top of that, we equip that quiver with the gluing operation over morphisms, and not just paths. This gluing operation over morphisms is most commonly called composition. In the context of categories, the words arrows and morphisms are all the same. Okay, they refer to the arrows of the underlying quiver of a category. Even if one constructs this category as described throughout this video, one may also construct it from this new underlying quiver instead, and making every path equivalent to a path with only one arrow of the underlying quiver, since its arrows are precisely the morphisms of our category. So, in case you zoned out from that explanation, let me summarize. Morphisms are arrows, and arrows are morphisms in the context of a category. Given that categories are a pretty natural extension of free categories, which themselves are a pretty natural extension of quivers, categories provide a very permissive and powerful way to describe structures, one even stronger than free categories and way stronger than quivers. Quivers were a good model for direct relationships and all. Free categories, on the other hand, help us see the myriad of paths from a point to another, allowing us to glue these paths, these free categorical arrows, which we couldn't really do with bare quivers. The categories, though, help us understand how two paths may be considered the same, essentially constituting a single entity that we call a morphism, allowing us to glue these morphisms together thanks to composition, and to understand how two distinct compositional procedures lead to the same morphism, the same class of equivalent paths. So, what can we conclude from this video? Well, in a way, structures can be modeled in different ways. Quivers, free categories, categories, as well as many more extensions and branches which I omitted to make this video as short as possible while driving the main devious point of that video home, that of introducing you all to categories, in the hopes that later on I'll make videos about more specific topics on category theory. As a bit of a cliffhanger, let me tell you that what this video shows is not even the start of what category truly has to offer. Its most important contribution is how easy it makes it to translate categories from one to the other, so that anything we can say in one category can be directly translated into another one. Category theory only truly starts when we introduce its most unique tool, what links categories with structures together, and we call these functors. To rephrase a famous quote from Back to the Future, you guys aren't ready for that yet, but you're gonna love it. So, yeah, I'll obviously make a video introducing functors in the near future. Honestly, I don't see how I could talk more about category theory if I didn't. As I said, that's where category theory truly starts, and I'm really not exaggerating. So, yeah, if that sounds interesting, don't forget to subscribe to get notified when that video comes out too. Or any other video comes out too as well. Whatever. As a final note, anyone who knows about category theory already knows I introduced categories in a quite non-standard way here. I did it this way for the following reason. I think it provides a more interesting flow, one that I hope helps newcomers understand the video more than it will have with the usual definitions. Since, associativity and identity morphisms and all are often just demanded as requirements while never being told why they're here. Given this definition, the very conceptualization of categories provided here makes the usual requirements much less arbitrary, I think. The very presentation of these concepts suffices to justify these properties. Everything here comes from somewhere, and I try to explain even the smallest of details. Though, for the video's flow's sake, I had to keep some explanations a little light, I do admit. But if you have any supplementary questions, don't hesitate to comment, and I'll try to reply to the best of my abilities. So, anyway, I hope you like this video. If you like logic, category theory, and math in general, because yes, that is math. I made you all learn math, one of the most advanced, important topics in math at that. Then, don't forget to subscribe to my channel. Or don't, I'm not your mommy. Having 3 digits in my subscriber count already boggles my mind anyway, so yeah. But I'm glad people like my content, so yeah, thanks. Really.